Section 4.8, L'Hopital's rule. So L'Hopital's rule is gives us a way of using derivatives to find limits. Before we used limits to find derivatives, but now we're kind of reversing that. If f and g are differentiable near a, and f prime of g is not equal to 0 near a, except possibly at a, and if the limit as x goes to a, f of x over g of x is an indeterminate form of type 0 over 0 or infinity over infinity, then the limit as x goes to a of f of x over g of x is the same as the limit as x goes to a of f prime of x over g prime of x. So if we can take the derivative, we have a limit of a fraction, we take the derivative of the top and the bottom separately, and then take the derivative of the top and the bottom separately, and then take the limit of the new quotient. And a could be finite, or it could be infinity. The rule also implies for one-sided limits too. So in this example here, we want the limit as x goes to 0 sine x over x. We saw this limit before, and we had an argument for doing that, but we can also use L'Hopital's rule. So this is indeterminate of the form 0 over 0. So the limit as sine x goes to 0, as x goes to 0, sine x goes to 0, and the denominator also goes to 0 here. So this is indeterminate of the form 0 over 0, and we can take the derivative of the top and the bottom. This is going to be the limit as x goes to 0. Derivative of sine is a cosine. Derivative of x is just 1. And now if we replace cosine as continuous, just the limit is the same as the value of the function there, that cosine of 0 over 1, and that's just equal to 1. So we saw that limit before, but this is another way of approaching it. Here's another example of how not to apply L'Hopital's rule. If we have the limit as x goes to 0, x minus 2 over x minus 3. Take the derivative, we get 1 over 1, which is equal to 1, but that's not actually the case, because in order to apply L'Hopital's rule, it has to be indeterminate of the form 0 over 0 or infinity over infinity, and this is not. This function should be just negative 2 over negative 3, which would be 2/3. The limit should be 2/3. So you have to be careful to make sure before you start taking the derivative of the quotient, make sure the conditions are met. Another example, limit as x goes to infinity of x to 3 over e to the x. This is indeterminate of the form infinity over infinity. So if we take the limit of the numerator, that goes to infinity, and the denominator also goes to infinity. So it's indeterminate of the form infinity over infinity. We can take the derivative of the top and bottom, and then take the limit of that quotient. So the derivative of x cubed is 3x squared. Each of x is its own derivative. And we still get infinity over infinity, right? If we take the limit, we get infinity over infinity. So we apply L'Hopital again. Limit x goes to infinity. Derivative here is 6x over e to the x. Still indeterminate. We get infinity over infinity. Take the derivative again. X goes to infinity of 6 over e to the x. Now we get 6 over infinity, which is equal to 0. Okay, so you can apply L'Hopital's rule repeatedly, now there are other determinate forms other than 0 over 0 or infinity over infinity, so some other determinate forms. We have infinity minus infinity, or 0 times infinity, or infinity to the 0 power, or 1 to the infinity power, or 0 to the 0 power. Sometimes we can manipulate these to get these in the form. We can't apply L'Hopital's rule directly, but sometimes we can manipulate them to get into one of the forms. We want one of the forms either infinity over infinity or 0 over 0. So this one, limit as x goes to 0 from the positive side, 1 over x minus 1 over sine x. Well, 1 over 0 is infinity. 1 over sine x, as x approaches 0 from the positive side, is going to be infinity. So this is indeterminate of the form infinity minus infinity. Let's see if we can manipulate this to get into one of the either 0 over 0 or infinity over infinity. We could maybe combine these fractions to get a common denominator. The limit x goes to 0 from the positive side, multiply top and bottom by sine x, and top and bottom there by x, and we'll get sine x minus x over x sine x. Okay, as x goes to 0, this is going to be 0 over 0. Now this is indeterminate of the form 0 over 0, right? We take the limit. This is numerator goes to 0 and the denominator goes to 0. So now we can take now we can apply L'Hopital's rule. Limit x goes to 0 from the positive side. Derivative of the cosine is a cosine, minus 1 over. Bottom we can use the product rule. X times the derivative of the cosine, which is derivative of the sine, which is the cosine, and then plus the sine of x times the derivative of x, which is just 1. Okay, so what happens now? So the numerator goes to 0, denominator also goes to 0. It's still indeterminate of the form 0 over 0. Okay, so let's apply L'Hopital's again. Limit x goes to 0 from the plus, and derivative of the cosine is minus the sine of x. So we could apply the product rule here. This is going to be derivative of cosine is minus the sine, so it's minus x sine of x plus cosine x, and then times the derivative of x, which is 1, and the derivative of sine is plus the cosine. Okay, so this limit x goes to 0 from the plus side minus sine x over minus x sine x plus 2 cosine x. Okay, so this limit will go. This is 0. This term 0. That term 0. This term is 1. So this is going to be 0 over 0 plus 2, which is equal to 0. So this limit is equal to 0. Okay, so we had to apply L'Hopital several times. We had to first initially get that in the form 0 over 0, and because we can't directly apply L'Hopital to infinity minus infinity, so we had to manipulate it to get in the form 0 over 0, and then we repeatedly applied L'Hopital to get the limit. Okay, limit as x goes to 0 from the plus of square root of x times ln of x. This is in the form 0 times minus infinity. So we can't apply L'Hopital directly. So again, we want to manipulate this to get the form either infinity over infinity or 0 over 0. We can rewrite this as limit x goes to 0 plus ln x over 1 over root x. Okay, so multiplying by root x the same as dividing by 1 over root x. Now, as x goes to 0, this will be minus infinity. Yeah. And this one is going to be infinity. So we can apply L'Hopital here. The sign doesn't have to be the same. You can have it the form minus infinity over infinity. That's fine. let's see, it looks like I'm frozen. My screen's frozen from there. Now I'm unfrozen. Okay, so let's apply L'Hopital now and take the derivative. Well, actually, let's write this in exponent form. X goes to 0 plus ln x over x to the minus 1/2. And if we take the derivative, that goes to 0 from the plus side. This is going to be 1 over x over minus 1/2 x to minus 3/2. So let's okay, so if we multiply top and bottom by 2, we get 2 over x over minus x to the minus 3/2. Multiply top and bottom by x to 3/2. We'll have the limit x goes to 0 from the plus side. This will be 2x to 1/2 over minus 1. And this limit is going to go to 0. So this is going to be 2 times 0 over minus 1, which is 0. Okay, so again, we initially we were not, the original function was not in the form that we needed to apply L'Hopital, but we were able to manipulate it to get it in that form, and then apply L'Hopital to get the limit. Okay, so other example, limit as x goes to infinity, x to 1 over x. So this is the form infinity to the 0 power. And again, we want to manipulate this to get in the form that we can apply L'Hopital. So we can do this, we can take limit x goes to infinity of e to the ln x to 1 over x. Okay, because exponential and log are inverse functions of each other, so they sort of cancel out. And then use the rule for exponent. The exponent can come out in front of the log. So this is the limit as x goes to infinity of e to 1 over x times ln of x. Okay, so this is ln x goes to infinity, 1 over x goes to 0. Okay, so this is, we can write this as, then, that's using the rule for exponent, because the exponent can come in front of the log. So let's rewrite this as limit x goes to infinity, e to the ln x over x. Now the exponent of e is indeterminate of the form infinity over infinity. And one of the properties of limits is that you can take it inside a continuous function. So we have a composite function here. Outside function is exponential. Inside function is ln x over x. And we can take the limit inside a composite function as long as the function is continuous. So we can write this as e to the limit x goes to infinity of ln x over x. And this is indeterminate form infinity over infinity. So we can apply L'Hopital and take the derivative, e to the limit x goes to infinity. Derivative ln x is 1 over x. Derivative of x is 1. So this is e to the limit x goes to infinity of 1 over x, and this goes to 0. Goes to e to the 0, which is equal to 1. Okay. So again, this example was not in the form where we could directly apply L'Hopital, so we had to manipulate it to get it in a form where we could apply L'Hopital. Okay, and another example. Limit as x goes to infinity, 1 plus 1 over x to x. So this is the form 1 to the infinity power. 1 over x goes to 0. So the inside parentheses limit goes to 1, and the exponent goes to infinity. Okay, so again, we want to manipulate this to get it in a form where we can apply L'Hopital. Let's do compose it with exponential and log again. We'll write this as limit x goes to infinity of e to the ln 1 plus 1 over x to x. We can write the exponent we can put in front of the ln, so we can write this as limit x goes to infinity of e to the x ln 1 plus 1 over x. And so this exponent is the form infinity times 0. So let's write this as write a fraction limit x goes to infinity e to the ln 1 plus 1 over x over 1 over x. So dividing by 1 over x is the same as multiplying by x. So now this is in the form, this exponent is in the form as x goes to infinity, we have ln 1, which is 0. Yeah, this is this is 0 over 0 now. And you determine the form 0 over 0. So so we can take the limit inside the exponential. So this is the exponential limit x goes to infinity ln 1 plus 1 over x over 1 over x. And take the derivative now of the top and bottom separately, applying L'Hopital. So the derivative of this is going to be 1 over 1 plus 1 over x times the derivative inside, which would be x to the minus x to the minus 2 power, and the derivative denominator is also minus x to the minus 2 power. So these will cancel. And then if we take the limit as x goes to infinity, this just goes to this limit goes to e to the 1 over 1 plus 0, which is equal to e to the 1, which is equal to e. Okay. Okay, another example. Limit as x goes to 0 from the plus side of x to the sine x power. This is of the form 0 to the 0 power. So again, let's compose it with exponential and log. So plus e to the ln x to the sine x. And the exponent can come in front of the log. So this is the limit x goes to 0 from the plus side e to the sine x times ln x. Okay, so so this is infinity times minus. This is 0 times minus infinity. So we can let's see if we can write this as limit x goes to 0 plus e to the ln x over the cosecant x. 1 over cosecant is the sine. So now we have infinity over minus infinity over infinity. Okay, so we can take the limit inside the exponential. E to the limit x goes to 0 plus of ln x over cosecant x, and take the derivative e to the 1 over x, derivative log is 1 over x, derivative cosecant is minus cosecant x cotangent x. Okay, so I like to express everything in terms of sines and cosines. It's easier to remember what's happening there. So the it would be minus cosine x over sine squared x, so this is the limit. Oh, this is the limit. I forgot to put the word limit in here. Limit. And then we can flip this fraction and change the multiplication. So we'll have sine squared x over minus x cosine x. And this is x goes to 0 plus. Okay, so it's still of the form, the indeterminate form 0 over 0. So let's apply L'Hopital again. This is 0 over 0. So this is going to be e to the limit x goes to 0 plus derivative sine squared. That's 2 sine x cosine x over, and we apply the quotient rule on the bottom, and this is going to be minus x times the derivative of the cosine, which is minus the sine, so it'll be plus x sine x, and then minus cosine x. Okay, so let's see what happens now. If we put in 0, now we're good. If we put in 0, we get 2 times 0 times 1 over 0 times 0 minus 1, and that's equal to 0. So the limit of that function is 0. Okay. I'll do a partial proof of L'Hopital's rule. Let f and g, oops, I lost my cap to my pen. Let f and b be differentiable and continuous functions with continuous derivatives on an open interval containing a, such that the limit as x goes to a f of x over g of x is indeterminate of the form 0 over 0. So this is, I'm not covering all the cases here, I'm just covering the case where we have an open interval containing a point A. So this, so the other parts of the proof will be similar, but I'm not trying to prove all the different cases. Okay, so because of continuity, f of a and g of a are both equal to 0, and so we can subtract f of a and g of a from top and bottom here, and it'll be the same. And then if we can divide, and also divide by x minus a. So this is as long as x is not equal to a, then the limit as x approaches a is going to be the limit of this quotient is going to be the quotient of the limit, and the limit of the numerator is just the derivative f prime of a limit of the denominator is g prime of a. So we're assuming the derivatives are also continuous, so that means that the limit of f prime of a is the same as the limit as x goes to a of f prime of x over the limit as x goes to a of g prime of x. And that's equal to the limit of the quotient is equal to the quotient of the limits, as long as we avoid denominator 0 here. So that's a partial proof of L'Hopital's rule. And that concludes this presentation.